Okay, so we left off last time after we had figured out the velocity of the center mass of this bicycle motorcycle model, and I've written all of that back here. We were using the two-point theorem, and we started with point B, which is in the ground plane, and we added this omega cross to R term. So I've written the velocity at P, and the key things are to note that V has a component in both the I and J hat, in the J and the K hat directions, and that there's only the U component in the I hat. And then we have omega that we have to be very careful to write because there's this R sine theta, R cosine component, and the R vector is pretty simple. When you do the cross product, you find that you have a I hat component, negative RH sine theta, and a J hat component, theta dot H. We put those together, and VC then looks like what I have there. It has U minus RH sine theta, V cosine theta plus theta dot H, and negative V sine theta. So that's going to give us the VC squared in that T equation for kinetic energy that I have. And then the right portion here is the kinetic energy for a single rigid body that only has these principal components of inertia. Principal components of inertia aligned with I hat, J hat, K hat. Alright, so VC squared is U minus RH sine theta squared plus V cos theta plus theta dot H squared plus negative V sine theta. And we can linearize partially by substituting out our sines and cosines for the small angles and roll. So we'll get that. And that'll just save us a little bit of writing as we move forward. So we've got the piece of the puzzle here to write the kinetic energy. So we can do that. I'm going to have just 1/2 mv squared, but then I'll go ahead and put in our omega components here so that we get I1 theta dot squared over 2 plus I2. This will be R squared theta squared over 2 plus I3 R squared over 2. And I've gotten rid of the sines and cosines there also. So we need to figure out potential energy also. We have a conservative force, gravity. And if we look at a rigid body here with our mass m, it's h above with a pendulum length here of h. then the height above the ground is h cos theta. So V is simply going to be the mass times gravity times the pardon me, height above the ground. And we can simplify that as mgh for small angles also. I'm sorry. Actually, let's not do that. Not simplify it yet. We do need to take the derivative with respect to theta. Okay. There are no non-conservative forces, so our generalized force is going to be 0 in this case. We don't have any other external forces that are acting on the system that we need to take account there. Alright, with all of that, you can figure out Lagrange's equation here. And I'm not going to do all the math, but you do your algebra, you do your calculus, and you're going to end up with an equation of motion that looks like this. Okay. So this is the full equation of motion that results. And I will come back after that.